Recording is rolling. It is Monday, October 7th. A bunch of you guys just turned in your dynamics puzzles and dynamics quiz, so I'll be grading those. Some of you guys turned in some of the stuff last week also, so good. You guys know, of course, there's going to be no school this Wednesday or Thursday because we got Hurricane Milton held it our way. So got probably today, tomorrow, and Friday. Thinking Monday, Tuesday, Friday. I'm gonna plan for. Picture retakes are this Friday. That applies to you. Friday the 11th. PSAT. Do you guys remember last week I was telling you guys a bit about this, saying this classroom is being used for the PSAT. It was originally supposed to be this coming Wednesday. Where did I tell you guys to relocate? Media Center, right? Of course, if you're taking the PSAT, then take it anyway, but everybody else relocate to Media Center, right? That whole thing's just been rescheduled to 8 days from now, Tuesday. Okay, so Tuesday, 8 days from now. Oh yeah, go ahead. Oh, they did. Okay, all right. So I'm being told it's rescheduled again to Thursday. Okay, so Thursday. So I'm going to remove this, and then yeah, if you're listening on the audio, so the word is Thursday probably. All right, sounds like it then. All right, so otherwise, same plan, just different day. All right, so we're starting new stuff today. New stuff. So let's show you guys in the thumbnails what's going to correspond to and what the topics are. So you guys remember the silver banners? This was scientific method, measurement, algebra, geometry. Then we did the red banners. That was linear motion and projectiles, so kinematic motion. Then you guys had 2 pages of these orange banners. This was Newton's laws of motion, free body diagrams. There were Atwoods, there were inclines, there were these tensions. Okay, so that's what you guys just turned in your quiz on. So the quiz was on those orange banners. Now we're moving on to this page. There's also 2 pages here of posters. Now there's some purple banners and there's some yellow banners. This has to do with, well, we're going to start getting to circular motion and rotation. Here, I'll list it out. So no, different textbooks. Here, guys, focus here. Different textbooks organize this information differently. I didn't always teach it like this. The last few years, it's worked out pretty good. We're going to do circular motion. You guys have turntables on your desk. So if they talk about the circular motion, if you want to get your hands on the turntable so you can see up close what exactly it's going to look like. Talk about things moving in circles. Now, maybe you possibly have a math plug on your desk that you can sit on there. Guys, as this goes around a circle, remember back to Newton's first law of motion. Remember, things only ever want to move in straight lines if they're moving at all. So if something's moving in a circle, do you think there's a force that's causing this to stay on the surface? What force is that? Friction. It is a friction force, isn't it? That's right. It is friction. Now that friction is acting, here's a new term, is acting as what's called a centripetal force. So this is called like a center-seeking force. Did I possibly a few weeks ago upload to Google Classroom a link to a Vsauce video called Spinning? I think maybe. Yeah, okay, I'm seeing some nods. Right. I might possibly link that again. It's really worth watching. It connects what we're about to do now to Newton's first law of motion back in the day. Also some stuff that we're going to save for December too. So it's all kind of in there. Okay? Well, we're also going to pretty soon in the next week or two talk about universal gravitation. So what's the force between you and the Earth or the Earth and the moon? What's that have to do with the size of the Earth, right? Like its mass, its radial size, right? Then we're going to take all these ideas, circular motion, centripetal force, gravitation, put it all together and create orbits. So kind of a hodgepodge of different topics, but they all kind of go together and they work well with the labs that we have. Okay? All right, so a bunch of little things. So that's what to look for. Probably about 3 weeks. So it's going to take about 3 weeks to do. Okay. I gave you guys some new puzzles. So here, since I'm using this video for all my classes, because we're all starting talking about new stuff, let me show all the puzzles. So for my AP students, looks like this says chapter 7 on it. I circled some there. For my conceptual students, there's chapter 8, there's some stuff, and then chapter 9. So we do a little bit of 8, a little bit of 9. And then for my honor students, I got chapter 6 is circular motion and chapter 7 is gravitation. So 6 and 7. So everybody has some pages there. I don't have a due date on those yet. Again, I think it's going to take us about 3 weeks to pace out all these topics. My AP students also have an AP classroom. I do have a tentative due date on that as a couple weeks from now on the 21st. Okay. All right. So I think we're, all right. So there's about the agenda. I think we're about ready to get going here. So there is a hurricane barreling our way. And actually that works really well with what I'm talking about here, because I can tell you physics of hurricanes. Yeah, you guys can go home and you're hunkered down in your houses with your parents and your siblings. You say, hey, I know the physics of why hurricanes form and what is that. So we're about to do that. That's gonna link to all this new stuff. And then what I did want to get started by the end of today is the rotational kinematic lab. Now, I did not give you guys this page. I did my first period class got this page. This goes hand in hand with this turntable. This could be this turntable, right? Right. So I'm going to look at kinematic motion, but in a rotational sense, like an angular sense. Right? Some classes have had like 2 to 5 minutes at the end of the day. So it's like it's kind of hard to get started on that. So hang tight on that. It's probably going to be tomorrow's activity, and that'll probably take us about to the hurricane. All right. So why do hurricanes form? What's the physics going on there? So it has to do with starting today, there's going to be 2 different kinds of speed. I can talk about linear speed, of course. That could be in miles per hour or meters per second. But there's also something to do with like how fast is a turntable turning. So I've got a map of the Earth here. I've also got a globe here, but kind of hard to fit the globe in front of the camera. So I don't know, so that goes great. But maybe the globe I can show you guys in class. And if you're watching this video at home, then here's the best I can do is to have a map of the Earth and have this thing spinning. Right. All right. So here we go. Suppose it's Christmas Eve and we're up here with Santa and the elves. You guys see that? We're right here on the North Pole. And it's time to break out the Santa cannon and start blasting presents straight south like we do every year. I think that's how that works, something like that. So pow, pow, you get a gift, you get pow, or blast all these presents straight south. Now, if you do that, if the Earth was not spinning, then would the presents just go like straight south? Straight south. That's all they would do, right? No problem, right? But, right, we're not on a stationary Earth. The Earth actually is spinning in space, right? So now let's give the Earth a spin. The Earth spins west to east, right? West to east. Now, if I move my finger straight south on the globe, okay, just go straight south, no problem, right? But if I throw in the spin of the Earth, then from our point of view up in the North Pole, where Santa with the elves, right, we're looking straight. Does it look like the presents are going straight south anymore? Looks like they're curving off which way? To the kind of to the west, right? Kind of to the west, right? Or from the point of view of the North Pole, that's kind of to the right. Looks like they're curving off to the right. Okay, let's show that same thing up here. So, right, if the Earth was stationary, they would just go straight south, no problem, right? But if you throw in the rotation of the Earth rotates this way. Now, let's put those 2 motions together. So all I'm going to do is just move this in a straight line according to Newton's first law of motion, but have the Earth spinning underneath it. And oh, look at that. Looks like it's like a curve off to the right. You see that? Okay. Does anybody know what is the name of that effect called? It starts with a C. Where you throw something in a straight line, it changes latitude, and it looks like it's curved off. It's called the Coriolis effect, maybe Coriolis. Right. I bet a couple of guys know that Coriolis effect. Right. Now that's going from north to south. What if you go south to north? If you go south to north, let's think about maybe the linear velocities of each. I got 3 Roosevelts here, right? You guys see 3 Roosevelts? Huh. Like how far are they moving? How fast are they moving? Like, guys, this guy right on the North Pole, how far is he moving? How fast is he moving? Zero. He's not going anywhere, and he doesn't have any speed, any linear speed at all, right? But do you guys see these that have some radial distance? They're moving further, and they're also moving faster. Like if I point a radar gun at them, that this guy out here is moving really fast compared to this guy, right? Actually, he's twice as far out. Do you think twice as far out? Do you think he's also moving maybe twice as fast in the radar gun sense? Huh? Or what if you take a speed gate and you're like, this flies under a speed gate? Maybe something like that. Right? So, so now this is going to correspond to like changing latitude. What if we're down here closer to the equator? Well, we blast a cannonball straight north now, straight north. Now, down here close to the equator, you're going almost 1,000 miles an hour to the east. And then if you're also headed straight north, now you're crossing latitudes, and the land up north is not moving as fast beneath you. So this cannonball's going too fast to the east. That's going to make it appear relative to the surface of the Earth to curve off also to the right. So if you change latitudes in the northern hemisphere, it looks like you're always curving off to the right. So you blast a cannonball south, curves off to the right. Blast a cannonball north, curves off to the right. You see that? Right? Because the Earth is spinning underneath you. Right? Everybody see that? All right. Now let's take this out to the ocean. Maybe somewhere out in the Atlantic, possibly, or how about the Gulf? And say we got the sun beaming down all day, and it's evaporating lots of water, right? So lots of evaporation, right? And there's lots of water vapor, pretty dense, heavy water vapor that's all evacuating a space because it's all evaporating. Guys, if you have large masses of water vapor evacuating a space, does that leave behind a high or a low pressure? If it's evacuating, like a vacuum, that'd be like a low pressure. So from above, here's like a meteorology term. Maybe I see a giant low pressure. You ever see meteorology? Like a giant weather map and see giant L, it probably stands for a low pressure. Okay? There's this low pressure sitting in maybe the middle of the Atlantic, middle of the Gulf. Right? Now, guys, if it's a low pressure, do you think all the air masses around want to fill that void? So all this air wants to rush in and fill that void for that vacuum. Isn't that true? Right? But you guys know that Coriolis effect, if you're crossing latitudes, it's going to curve off to the right, curve off to the right, curve to the right, curve to the right, curve to the right, curve to the right. Right? Wouldn't it be doing like that? Right? Now from above, that means that these air currents are going to spin which way? Clockwise or counterclockwise? You guys see counterclockwise, right? You guys see it? Counterclockwise? All right, let's take a look. So I switch my screen over here. Start with, all right, here. Here's Milton. It's going to be headed straight towards Florida. It's in the Gulf. Hey, it is spinning counterclockwise, isn't it? You guys see that counterclockwise motion? Do you guys think that all hurricanes that cross over Florida have to spin counterclockwise? You pay real close attention, they do. Okay? So all these hurricanes are spinning counterclockwise. Guys, where are the worst tornadoes in the entire world? Tornadoes. Or like Tornado Alley up in like Texas, Oklahoma, Nebraska type area, right? Do you think that most tornadoes also spin counterclockwise from the top? Yeah, it turns out they do. Now, tornadoes are small enough systems. Sometimes you can get backwards tornadoes. I think it's like 5 to 10%, something like that. But yeah, most tornadoes and all hurricanes in the northern hemisphere, they have to spin that way. Hey, let's do a video. Got kids on a merry-go-round. You guys see this yellow ball right here? They're going to be passed around this yellow ball. Now, you guys know Newton's first law of motion. If something's in motion, does it just want to keep moving in a straight line? Right. So if I held a meter stick up to the video, right, let's rewind a little bit. Right, watch this yellow. Right. So do you guys see that yellow ball was just moving in a straight line? Right, rewind again. Right. It's real fast, but it just moves in a straight line. Straight line, boom. Right. Now the camera's point of view is in what's called an inertial frame of reference. The camera is stationary, or if it was moving, and then it would just be a constant velocity. Right? So that's inertial frame of reference. So yeah, we see the yellow ball is following Newton's first law of motion, law of inertia, just goes in a straight line. But what if you change your frame of reference and now you're sitting with those kids on the platform? You guys ready to? You guys see that? Does that ball look like it's going in a straight line anymore? No, right? But it is. That ball right there. Is that ball going in a straight line? Turns out it is from an inertial frame of reference, but you wouldn't know that if you're sitting on the moving platform. Looks like it's going in a circle, right? That's also called the Coriolis effect. I think this video is called Coriolis force. Sometimes you hear it called that, but it's not really a force. It's more like just an effect. Oh, whoops, got some other videos queued up, but I'm gonna switch out of there. So I'm trying to switch my screen back. All right, there you go. Yeah, so that's hurricanes. Right, so you got a low pressure combined with the rotating Earth, and boom, you got a hurricane. Ooh, what about this? Suppose you go down to Antarctica. We're gonna switch hemispheres. Go down to the southern hemisphere. Let's say it's War of the Penguins. The penguins break out their penguin cannon, and they're gonna declare war on the entire Earth. They start blasting cannonballs from Antarctica. Now, if they blast it straight north, and the Earth wasn't spinning, it would just go straight north. But let's put a spin on the Earth. So Earth rotates this way. All right. Now, from the penguin's point of view, here I'm just gonna trace my finger straight north while the Earth is spinning. It appears that the cannonball is actually being deflected which way? To the left. Which is like west way, right? Hey, that's like backwards of the northern hemisphere, isn't it? Right. So it turns out, yeah, you go down to the southern hemisphere, and this whole thing reverses. If there was a hurricane that hit Australia, I guess it'd be spinning the other way, clockwise, wouldn't it? Okay, something like that. All right. So what I've been showing you guys is there's a discrepancy between maybe these two different kinds of speed now, right? Now, we've been doing linear motion for a few weeks, but now we're going to open up this rotational motion, right? And there's rotational equivalents, all these things. It's just saying how fast is something going in miles per hour, meters per second, which has been our focus for, well, up until today. Okay. Now we're going to say, how fast is this turntable turning? How fast is the world spinning? This is Greek letter omega. And it's going to be angular velocity that quantify radians per second. Did you guys notice? No matter where you're standing on the Earth, everybody has the same turns per time. Everybody has one rotation in 24 hours. Or I should have asked you guys that. You guys would have said that, right? The Earth spins one rotation every 24 hours. Could that be an angular speed for the Earth? Angular speed? Okay. Do you think you could convert that to how many degrees per hour if you wanted to? Right? Or radians per second for that matter? Right? Right. But depending on your latitude, you have all different linear speeds. Down by the equator, it's almost 1,000 miles an hour. Up in the North Pole, it's about 0, right? Relative to the spinning Earth, right? So yeah, when you change latitude, you have the same angular speed but different linear speed that's set up for the Coriolis effect also, right? All right. So I think I pointed out your thumbnail notes. There's some purple banners, some yellow banners. Let's focus on the purple banners today. Purple banners, well, or a bunch of them. So here we go. All right. When you guys see theta, you guys have seen this character before. Wasn't that one of the first labs I had you guys do was measure some triangles with a protractor? And we're just like, hey, what's the size of that angle? The size of that wedge? Actually, you guys have used this tool quite a bit in this class. What's the size of an angle? In general, I could call it theta. And starting today, maybe I'll try to tend to reserve that for how far is this turntable turned? How far is it turned? Right? Could be. Now, guys, how far is something turned? Could you quantify that in degrees? You probably could, right? It's turned like 15 degrees. It's turned, 360 degrees. That'd be good. Could you quantify that in like rotations or revolutions? Probably do that too, right? But what did I type here? Guys, RAD, rad. That's short for something. That's short for what? Radians, radians. Okay. Now we haven't really touched radians yet in this class, but we are starting today. This is more like a mathematically pure way to describe angles. Yeah, you could do degrees, you could do revolutions, but radians. Now, what's special about radians is that I have some equations coming up in some of these other posters. Whenever you directly multiply or divide an angle in a math formula, it has to be in radians. Okay, that's going to come up later today. If you've ever paid real close attention, have you guys ever noticed anytime you've ever plugged in angle in degrees into an equation in this class, it has always been inside a trig function. Like for example, sine of 30 degrees. And then if the calculator is programmed in degrees, it'll say, oh yes, it's 0.5, exactly. But notice that's inside a sine function. You see that? Right? Can you multiply an angle directly by something outside a trig function? Only if it's in what unit? Radians. Has to be radians. Okay, hold on to the idea. You'll see that later. Okay, how fast? Omega radians per second. This is angular velocity. I might call it rotational velocity. How fast is something rotating? So the Earth could do one revolution every 24 hours. Maybe this turns like so many degrees every second. But the mathematically pure way to describe that could be radians per second. Okay, look at that. We got. I haven't even told you guys what 1 radian is, but here, that's coming up real soon. I'll show you guys what 1 radian is. Okay, hold on to this idea. It's just right now, it's just a way to measure an angle. Okay. Guys, could this turntable be speeding up or slowing down? If it starts from rest, you speed it up, or if you let it go, maybe there's a frictional fork and it slows it down. Slows it down. Okay. That could be changing some radians per second per passing second. I'm going to call it radians per second squared. Okay. Oh, and that's Greek letter alpha. You've seen that character before, but this week, next week, I'm going to try to reserve it for this property, right? Angular acceleration, also called rotational acceleration. Okay. Oh, yeah, Lisa. Oh, yeah. Go. All right. All right, a couple more here. You guys see these 2 gold rows. All right, this is a little bit different type physics. How about oh, I think I asked you guys this before, but I forget because we're like halfway through the day. I forget what questions I asked. Did I ask you guys if you're rotating this, what force is actually keeping this on the surface? What did you guys say? Said that was friction? You guys said that was friction, right? Okay, so that's acting as what's called a centripetal force. It's like a center-seeking force. And if you hadn't watched that Vsauce video yet called Spinning, I think I'll try to link that again today. Take a good look at that. Okay. How about one of the labs that's coming up pretty soon? Actually, I printed it on the back side of this lab page I'm going to give you guys tomorrow. Is a centripetal force lab. Because what if you do this? What if you have a ball on a string and you're flying that ball around in a circle pattern? You guys think there's some tension in that string? Tension in that string, holding the ball in a circle? That's also acting as this kind of force, centripetal force, center-seeking force, right? Have you guys ever been in a car? You go around a really tight curve a little bit too fast. You feel thrown to the side. Whoa, feel some G's. Can you guys feel that? That's this right here. It's centripetal acceleration. It is an acceleration. It's still in meters per second squared, just like this force is still measured in newtons. But it doesn't actually have to do with changing speed. It has to do with changing direction, like going around a curve. Okay, you guys get that? All right. Now the bottom half of this table, we're actually going to save for December. So I'm not going to talk about some of these things for a few months, right? But you see it, and you say, oh, okay, I see those terms. I know it's coming up in December. Okay. All right. Next slide. This is not too different, but here, let's look at rotational analogs. So what was going on in linear motion and what's going on in rotational motion? What's sort of the equivalent? Now, time in seconds is still time in seconds. You might have some stopwatches out. We're going to use these stopwatches tomorrow as part of that kinematic motion lab. Okay. Instead of saying how far something moved in meters or miles or feet or whatever, right, meters, okay. Now we're going to say how far is that turntable turn? And if it's going to be in a math equation, then I really want radians, although you could also do revolutions, degrees, could be the same idea. Radians is really good this week, right? Instead of saying how fast is a car going in miles per hour, meters per second, now I'm going to say how fast is a turntable turning in radians per second. Instead of saying, is the car speeding up or slowing down in a linear sense, is that turntable speeding up or slowing down in an angular sense? It could be alpha, it could be in radians per second squared. Okay, so you got theta, omega, alpha. You guys got this? Okay. All right. So you guys know you have thumbnail notes on all these too. So you guys have this printed out. Now the bottom half of this table is, again, we're going to save this for December. Here, I'll point out one real fast, so you're not going to see it for a while. But you guys remember how mass in kilograms is represented how much inertia something has? It turns out if you put something on a rotating platform, it's not just how much mass, but it's also where's that mass located. This is the sum of mr squared. It's called rotational inertia. So again, we're not going to see that for a while, but in time you'll see that one, right? Right. Then we have torque and angular momentum, and okay, so this will be later on. All right. Right. Aha, turntable time. Okay. You guys, do you see this could represent the turntable? Let's get that turntable back out. All right, turntable. And I'm going to put 3 Roosevelts on this turntable. Okay. So one right in the middle, one kind of halfway out to the edge, and one pretty close to the edge. Okay. Let's get some measurements. Let's get some radial distance from the center. Okay. So this one's right at the center. It's 0 centimeters from the center. So 0, 0. This one's about 7 centimeters out. This one's about 14 centimeters out. Ah, okay, guys, 14 compared to 7 centimeters. That's twice as far out from the center, isn't it? Twice as far out. Say you give this a spin. Okay. Let's see if you guys are following so far. So, guys, do all 3 of these Roosevelts right now complete the same number of turns in the same amount of time? Do they all have the same turns per time? Yep. I bet they make all 1 revolution in however many seconds it takes me to make 1 revolution. Does that mean all 3 of these have the exact same angular speed? Angular speed, turns per time, radians per second. Yep, they're all 3 the same, right? Just like anywhere you stand on the surface of Earth, you make 1 revolution every 24 hours. Right? What about this? What if I point a radar gun at each of these 3 guys? Let's start with the guy right in the middle. If I point a radar gun at this guy, how fast is this guy moving right now? 0 meters per second. Then, do you guys think this guy has some speed? Or what if he had one of those speed gates? And this goes through a speed gate. He's going to read some speed. What about this guy out on the edge? Hey, this guy's twice as far out as this guy, twice as far away from the center. What do you think this guy's speed is compared to this guy's linear speed, meters per second? Do you think it's twice as much? Twice as much, you guys think? Huh. I think it might be. Hold on to the idea because I want to back that up with a formula. Just plant some ideas now. Okay? What about how far have they moved? Let's look at what if I had a circular racetrack? Can you guys imagine some circular racetracks? Like there, we got 3 Roosevelts all racing around a circular racetrack. You see that? Okay. So how far, let's say I give this one complete rotation, one rotation. How far did this guy right in the middle move? Nowhere, 0 meters. Okay. Now this guy moves some distance. Maybe this guy moves some distance. Hey, guys, if it's one trip all the way around the circle, one trip around the circle, that's called one what? Starts with a C. The what of a circle is all the way around. Circumference, right? Circumference, right? Huh? Circumference. Hey, what is, guys? What is circumference relative to radius? Circumference relative to radius. Do you guys know? Circumference equals, huh? Circumference equals, hold on to that idea. I'm just going to redraw this right here. Let's get this circle going right here. Right? Because I want you guys to make some connections. This is all going to come together. Right? Let's say I draw one radius right here. You guys see it's one radius? Maybe I could measure that with my ruler. It's like, oh, it's about 5 centimeters. What if I cut a length of string that's exactly that long, about 5 centimeters? I start winding that around the outside. You think it could get to probably right about here? You guys think that that distance right there is about the same as that? You guys pretty close? Pretty close, you guys think? Right. I'll call that R also. Is that all right? Right. Now, that's going to create a wedge of some size. I'll call that theta. Right? You guys see that? Right. That theta is equal to, all right. Remember I told you guys that I was going to tell you what 1 radian was? 1 radian? Do you think that's that right there? 1 radian? Right there? You see it? Right. Hey, I wonder how many degrees that is, like with a protractor. With a protractor. Take a guess. Guys, take a guess. How many degrees do you think that is? Just kind of eyeballing it. My picture might not be 100% scale. I just kind of slapped a made up circle there. Huh? Do you think it looks about maybe between 50 and 60 degrees, about 50 to 60 degrees? Right? Let's get an exact value. Guys, all the way around the circle, how many degrees is that? 360, right? 360, right? And oh, whoops, there's something I forgot to set up before. Oops, right? Here, let's go fill in some details. Fill in some details, right? Let's do circumference. I need to come back to circumference. We need a formula for this. Guys, what's a formula for circumference? Did you guys say? Circumference equals 2 pi r, right? Right. So I know the area of a circle is like pi r squared. I'm not so much concerned about that one, but the circumference is 2 pi r. Guys, remember, r squared is like an area, hence area. Radius is like a linear distance, hence circumference could also be a linear distance. You guys remember that? Right. Right. So what I want you guys to see is that what if you wanted to go any distance around the circle? Because one circumference is one very specific distance. That's exactly one round trip all the way around, right? But what if you wanted any distance, right? That's this formula right here. You guys see this one? It says x equals theta r, right? Do you guys see that it's 2 pi? Is that like 6.28? Here, watch this. Watch how many wedges I can fit around the circle. There's one wedge, obviously, 1 radian. There's 2, there's 3, 4, 5, 6, and then I'll have a little bit left over. Ooh, guys, 6 point. Oh, wait a minute. I was gonna ask guys. 2 pi. 2 pi is equal to about what number? 6.28. Pretty close, right? I can fit 6 wedges, and then there's a little bit left over. Right, so it's like 2 pi of these radians. Okay, so this circumference equals 2 pi r is a very specific version of this more general formula. X in general, if I want to go any amount around the circle, is equal to, in place of 2 pi, it could just be any general angle theta times however far you are from the center of r. Now, the catch is, though, this angle theta has to be in what unit? What unit? Can it be degrees? No, radians. Has to be in radians, right? Like 2 pi radians is 360 degrees. 2 pi radians is 360 degrees. Is one revolution, one rotation, one revolution. You'd say, okay, so something like that, right? So 2 pi radians, 360 degrees, same thing, right? which makes me think, what is 1 radian? What is 1 radian? Okay, that's the question I was rounding back around to. Okay, 1 radian. What's the size of this wedge? Remember, it's about looks about 50 or 60 degrees, something like that. Is that right? Well, if 360 degrees is all the way around, and 2 pi of these radians is also 1 trip around, how many degrees per radian? Can we just divide those two numbers and see? Here, try it out in your calculator. Let's do this. Take 360 degrees, because I want how many degrees per radian. So I'm setting up a fraction here. Divide by, open parenthesis. And how many radians did we say was equivalent to 360 degrees? 2 pi, right? As in circumference equals 2 pi r is a specific version of x equals theta r. That's for 1 round trip. Right, close parenthesis. Okay, there we go. I'm taking 360, I'm dividing by, and then make sure your 2 pi is in parentheses to get this right. You're getting about, there we go. 1 radian is approximately 57 degrees. There you go. Right. So there you go. Whenever I say 1 radian, which we talk about radians a lot for the next few weeks, whenever I say 1 radian, think about 57 degrees. It's about that wedge right there. Right? If you and 5 friends show up to, hey, let's say you have a hurricane party. It's like you and 5 friends. And so there's 6 people all together. And you take a pizza and slice it into 6 equal slices. Every slice is pretty close to radians. It's a tiny bit more than 1 radian, wouldn't it be? Right, true? Every slice would be 60 degrees. That's a tiny bit more than 57 degrees. Okay? You guys see that? All right. So everybody good with that? All right, so here, quick recap. You guys know circumference equals 2 pi r is exactly 1 trip around. But now you have a more general formula. I bet you guys have known circumference equals 2 pi r since like 5th grade. Okay? Now you can go any amount around the circle you want to go. X. I could say any amount x. And just take the angle in radians times your distance from the center. Okay? Like these 3 Roosevelts, like something like that. Okay? The further out, the further you walk around the track. Okay? I know 2 pi radians is equivalent to 360 degrees, is 1 revolution. Those are all the same thing. Which, by the way, that works out to 1 radian is about 57 degrees. Okay? There you go. Just a quick recap. Okay? Now, that could be for how far, like circumference equals 2 pi r. Right? You could also take rates of change. Let's talk about rates of change. Because if I say, what is the rate change in your position? That's a very fancy physics way of saying, what is your what? The rate change of your position is your velocity. So the rate change of x is v, right? Oh, and okay, there you go. And the rate change in theta, like how far have you turned, is how fast are you turning? Hey, look at that. Right? And you can also do the same thing for acceleration. Here's linear acceleration. Here's angular acceleration. So if you ever want to go on a turntable from angular motion to linear motion, all you have to do is very simply multiply by r, which is your location from the center. And if you want to go the other way around, if you know, say like you're on a circular racetrack and you know how far you've gone, and you want to figure out like, oh, I wonder what angle this is, all you have to do is divide by r. And same thing for these other ones. If you want to go from linear to angular motion, all you have to do is divide by r. You guys can do that too? Okay, so now you can go back and forth between angular and linear motion. Boom, boom, like that. You guys do that? Yeah, so remember the context of this. What this v is sometimes called tangential velocity, or this a could be tangential acceleration. So it's like if you were going in a straight line, what would your instantaneous speed or acceleration be, like in a linear sense? Okay. All right, so you guys good there? Okay. All right, you guys ready for some more formulas? More formulas. So we're talking about kinematic motion, say on a turntable now. We got, rotational kinematic formulas. These should almost kind of look familiar. Do you guys remember from a few weeks back, like x equals v naught t plus half at squared, and then v final equals v initial plus at, and v squared equals v naught squared plus 2ax, right? Now, if you just plug in the rotational equivalents of these, you get 3 new valid formulas. You got theta equals omega naught t plus half alpha t squared, omega final equals omega initial plus alpha t, and omega squared equals omega naught squared plus 2 alpha theta. Just like that, right? And I have 2 versions of this poster. This one's with the units. You guys see the units are written underneath, right? There's also without the training wheels there, without the units there. Right? So one of those, I think I put in your thumbnail posters. Okay. Let's look at units a little bit. Let's do a units type review. Okay. So guys, theta is quantified in what this week? Radians. That's a radians, right? Okay. Omega, angular velocity. What's the unit for that? Radians per second. So I have radians per second. And see, it says multiply by time, which could be in seconds. Guys, what is radians per second multiplied by seconds? Radians. How about this over here? Okay, 1/2, that's just a number. Oh, angular acceleration could be in what unit? Radians per second squared. Okay, and then times t squared, that could be seconds being squared. Guys, what is radians per second squared times seconds squared? It's also radians. Hey, guys, can you do radians plus radians to give you radians? Could you do that? Radians plus radians makes radians. You see that? Okay. This is something that I was emphasizing way back in the beginning of like a few weeks ago. You can only add together like units. You guys hear that? Did I ask you guys a question? Like, what is 3 miles plus 4 gallons? Did I ask you guys that? And what was the answer to that? That doesn't make any sense. Like, Griffin, you're losing your mind. You can't add 3 miles to 4 gallons. It doesn't make any sense. Now, can you multiply and divide different units? Yeah, that's okay. But you cannot add or subtract different units. That wouldn't make any sense. So here, I'm really just emphasizing this point. You guys have seen this from before. For any formula you've ever done in this class, you can only add like units together. In this case, radians plus radians makes radians. Is that okay? Same is true for these other ones also. You got radians per second, radians per second. Now, radians per second squared times seconds is also radians per second. Hey, right, and then this last one works too. Okay, you're set. All right. Next question relates also to these. We'll write down the linear version. You guys remember x equals v naught t plus 1/2 at squared. I mean, you guys have used these formulas so much at this point. Linear motion, projectile motion, and then in dynamics, these never went away. You're probably starting to memorize these just from using them over and over. Right? Theta equals omega naught t plus 1/2 alpha t squared. Okay, it's now a new looking one, but it's not completely new. It's just the turntable version of this kinematic formula. All right. Okay, show hands. How many guys right now are taking calculus? Who's taking calculus? Oh, okay. So I'm just gonna go ahead and do this because I'm doing this video for all my classes, but I've had a few students in a lot of my classes that are taking calculus. So calculus is about rates of change, like instantaneous rates of change. Well, that's what a lot of calculus is about. So let's talk about rates of change a little bit, because here, again, if you're watching this video at home and you're in calculus, then we're about to make a connection here that I wanted to say for about this point in the year. I wanted to wait until you guys had done derivatives, which is like an instantaneous rate of change. So let's talk about that. Right. But maybe even if you haven't had calculus, I bet you could answer some of these questions. Guys, what is the instantaneous rate of position called? What's that called in physics? The velocity, right? Instantaneous rate of position is velocity. Let's take this linear kinematic equation. Let's find an instantaneous rate of change. Now, the calculus notation looks like this. Dx over dt. That's just saying the rate change of your position with respect to time. And if that was changing itself, then it would just be like small changes at a time, right? But in physics, that's just called v, okay, velocity, okay? Equals, okay. Now, your initial velocity could be anything. It's supposed to like 3 meters per second, and then times time. Now, if you take a time rate of change, there's a calculus rule that tells you, you're in calculus for a few weeks, and then eventually you learn certain shortcuts for taking rates of change. What it ends up being is just that coefficient, right? So if it was 3t, I took the rate change with respect to time, it would just be 3, right? But in general, it could just be v naught in that case, right? And then there's a rule for exponents. So if I have an exponent on my variable, my independent variable, like 2 in this case, because it's squared, I bring that down in front. Guys, what is 1/2 times 2? Is that just 1, right? So I got a 1, I got some acceleration a, and then I got my variable t. But then what you do is you subtract 1 from that exponent. Like here, 1 minus 1 is 0, so it went away. Guys, what's 2 minus 1? Just 1. Okay, so that could just be that. Hey, look at this right here. Oh yeah, look at that. V final equals V initial plus AT. Hey, that's the second kinematic formula, isn't it? We do the exact same thing for the rotational version. So now we're on a turntable. How far is the turntable turn? Okay. Now, what's the rate change of that? It can be d theta over dt, which I'm just going to call omega, right? So how fast is it spinning is equal to, okay, omega times t. The time rate change of that is just omega naught, how fast it was spinning, plus, okay, 2 times a half is 1. I got an alpha. I got a t, and then 2 minus 1 is just 1, so that's a power 1 up here. Right? Hey, look at that. That right there that I just boxed in, that's the second kinematic formula right here. It's the same thing. So there you go. If you're in calculus, you know exactly what I'm talking about. We made some connections, and if you're going to take calculus one day, then think back to this. Oh yeah, that connected back to physics because it was like a time rate change or something. Okay? All right, so you guys good so far? It's good. All right. So we got next keyed up here. All right. Well, I was getting pretty close to this lab. Let's do a few things these last few minutes. All right. One is right. Tomorrow I will give you guys this lab page on the back. By the way, is a different lab. We're gonna save for later. It's about centripetal force. It's gonna be an important one, right? But we're gonna start with this rotational kinematic lab. Right. You guys have these turntables on your desk, so you can have either one of these bass slugs or one of these coins. Okay? And if I give this a rotation, I want to know what is its like linear type motion? How far is it moving? Say like around a circular racetrack, how fast is it moving? Yeah, like a speed gate on it. What could possibly its acceleration be if it was like slowing down to a stop? Right? And also its angular motion, its rotational motion. Right? So how many degrees does it turn? Except maybe I want to express that in radians. How many radians has it turned? The whole turntable. Right? How fast is it spinning? And if it's slowing to a stop, how could you quantify that? Right? Now that connection, guys, what's the connection between angular motion and linear motion? You just very simply multiply or divide by what? This radial size, right? This radial distance. So maybe I want to measure, what is this radial distance? I got 7 centimeters to this guy, maybe 14 centimeters to this guy, something like that. Right? And there's places to record this all on this lab table. I'm just showing you guys this today so that when you walk in tomorrow, you'll have been able to sleep on this for a night. Like, oh yeah, okay, here's what to look for. So we're going to quantify right away, what is the radial distance from the center? And then figure out a bunch of motion about this. Suppose I give it like 3 complete rotations. How far does it turn and how much time? You guys are going to have some stopwatches. Therefore, how fast was it spinning? And then what's the linear equivalence if you know where it's positioned? How far had it moved and how fast was it moving if you point a radar gun at it? Or what if I give you a speed gate? And zoom, zooms through a speed gate. Maybe we do that. Right? Then if you let it slow to a stop, slow to a stop. Sounds like an accelerating situation. Then a bunch of graphs. Oh, look at what we have here. X versus T, V versus T, A versus T. And now here's going to be the rotational equivalence. Theta versus T, omega versus T, alpha versus T. So like for turntable physics. Okay, you guys got that too? All right. Okay, and I think I got just enough time to show you one more thing. All right, let's switch over here. Let's do, all right, let's do Foucault pendulum. Let's skip this one. This is the time lapse one. Let's do the regular time one. All right, here, this one right here. Has anybody ever seen one of these? Maybe some of you guys. Where'd you guys see one of these? Okay, yeah, Science Museum. All right, Science Museum has these because I know I think UCF has one of these, and I think USF also has one of these. Right, it's called a Foucault pendulum. Now, is the pendulum? Do you think the pendulum is just swinging back and forth all day, every day, just swinging back and forth in a straight line? Right. But what's rotating underneath it? The entire Earth, the entire planet Earth. Right. So if you're standing in the room, what it looks like is it looks like the pendulum is changing orientation over the day. And so here, if I zoom closer to the end here, you guys see this next peg is queued up to be knocked over. Right. So and I see these have all been knocked down. So it looks like this pendulum is kind of rotating clockwise over the course of a day, which might tell you what hemisphere you're in. I think it's going to correspond to the northern hemisphere. Right? But yeah, but the pendulum actually is not changing orientation. It's just the ground. There it goes, knocked over that peg. It's really the ground beneath it that's changing orientation over the day. Right. So let's see if I can do the time lapse one. It's going to let me. Whoops. or too far. Skip past. All right. I don't know why this is being like super laggy. Has been since this year started. That they did like a software update. All right. Here's the time lapse version. Ah, there you go. Okay. Again, I can tell you what hemisphere you're in. If you keep real close to track the time, you can also get an idea of what latitude you're at. Okay, so here's why. Do you guys think this would work really, really well, like sitting on the North Pole? Because every day it would go completely round once on the North Pole or the South Pole for that matter, probably just opposite way. Okay. Do you guys know the country Ecuador is like sitting right on the equator? Okay. What if you had a science museum in Ecuador and you had one of these Foucault pendulums? How well would that work? It would just go back and forth, right? It would be like really boring, right? Maybe you could prove that you're on the equator, right? But it wouldn't really have that rotational type motion to it. It would just swing back and forth all day. Ecuador. All right. So there's a good pause point today. We're going to wrap up this video. All right. You guys have a good day.